Making a chemical by a large-scale industrial process is very different to making it in a lab. Many aspects must be considered to produce the chemical safely, sustainably, and economically.
Ammonia is an important industrial chemical. It's produced at a rate of 131 million metric tonnes a year. Scientists have fine-tuned the process to make ammonia under the most favourable conditions, known as the optimum conditions. The industrial process of making ammonia is called the Haber process.
On an industrial scale, the following reaction conditions are used: a temperature of 450 degrees Celsius, a high pressure of about 200 atmospheres, and the use of an iron catalyst.
The Haber process is a reversible reaction. The reversibility of this reaction is the main factor in determining the optimum conditions. The conditions are determined by the delicate balance between rate of reaction and percentage yield. The percentage yield is the percentage conversion of reactants into products.
To determine how the yield is optimized, we need to understand all the factors that affect the position of equilibrium.
You should be able to apply these principles to any reaction if you're provided with the data, but here we'll illustrate them with the Haber process.
First, let's look at the effects of temperature. In a closed system, the reaction reaches a state of dynamic equilibrium. This is where nitrogen and hydrogen react to form ammonia, and at the same time and same rate, ammonia molecules break down again to form nitrogen and hydrogen.
The forward reaction is exothermic. When 2 moles of ammonia are made, 92 kilojoules of energy are released to the surroundings. The backward reaction is endothermic and takes in 92 kilojoules of energy from the surroundings.
In general, for a reversible reaction, increasing the temperature moves the position of equilibrium in the direction of the endothermic reaction. For the Haber process, increasing the temperature moves the position of equilibrium in the direction of the backward reaction. This means that the breakdown of ammonia would be favoured over the formation of ammonia. Therefore, increasing the temperature would decrease the yield and less ammonia would be formed.
Now let's consider the effect of pressure on equilibrium. Increasing the pressure moves the position of equilibrium to the side with the least number of moles of gas molecules.
In the Haber process, according to the equation, the forward reaction produces 2 molecules of gas. The backward reaction makes 1 molecule of nitrogen and 3 molecules of hydrogen. In total, that's 4 molecules.
If the pressure is increased, the position of this equilibrium favours the direction that makes 2 molecules of gas, which is the forward reaction. So increasing the pressure increases the yield of ammonia.
The concentration of reactants and products also affects the position of equilibrium. In general, removing a product moves the position of equilibrium to the right, and adding extra reactants also moves the position of equilibrium to the right.
In the Haber process, products are continually removed as they're formed and the reactants are continually added. This ensures that the forward reaction is favoured and that the yield of ammonia is high.
The effect of a catalyst on the position of equilibrium is simple. A catalyst doesn't affect it. Catalysts just increase the rate that equilibrium is attained.
So far, we've considered the position of equilibrium. Now let's look at how conditions affect the rate of reaction.
Increasing the temperature increases the rate by increasing collision energy and frequency. Increasing pressure also increases collision frequency and therefore increases the rate of a reaction. Catalysts also increase the rate of reaction.
The optimum conditions for the Haber process are a balance between rate and yield. We want to produce an acceptable yield in an acceptable time.
The optimum temperature is 450 degrees Celsius, which is a compromise between a fast rate of reaction and high yield. High pressure favours both rate and yield, so high pressure is good. The only compromise here is that high pressures are difficult and expensive to maintain.
Hopefully you now understand the principles of how reaction conditions affect the economy of an industrial process, and now feel able to apply them to other reactions.
The contact process uses another reversible reaction to produce sulfuric acid on a large scale. Sulfur dioxide reacts with oxygen in a reversible reaction to produce sulfur trioxide.
The sulfur trioxide produced is used to make sulfuric acid. The optimum conditions for this reaction are atmospheric pressure, a temperature of 450 degrees Celsius, and a vanadium oxide catalyst.
Let's finish by looking at the Haber process in more detail. This is such an important process because the ammonia formed is used to make fertilizers, which the world depends on for food production. The raw materials for the process are nitrogen and hydrogen. Nitrogen is obtained from the fractional distillation of air, and hydrogen comes from natural gas. In reality, the gases don't stay in the reactor long enough to actually reach equilibrium, because they're being continually added and the ammonia produced is removed. Any unreacted starting materials are recycled. There are high energy requirements to achieve a temperature of 450 degrees Celsius and maintain the high pressure of the reaction.
The current Haber process is not sustainable. This is because the hydrogen and the fuels used to provide the energy for the process don't come from renewable sources. Scientists are currently researching alternative catalysts to iron that mimic natural enzymes to allow the reaction to occur at lower temperatures. This would make the reaction at least more sustainable, but we have a long way to go.